You see that incredible Earthrise photo? That blue marble just hanging there.
Yeah.
It really makes you stop and think, doesn't it? How did this place even come to exist?
It's an amazing shot.
Yeah.
Totally perspective shifting. And yeah, that question, how did Earth form? How does it work?
Yeah.
That's exactly what we're diving into today.
Right. We're going beyond just looking at the pretty picture. We're digging into a really solid source. Earth. Portrait of a Planet, the 6th edition. Think of this as our guided tour through Earth's origin story using this great text.
Exactly. Our mission really is to unpack how Earth formed and what makes it tick, based on what's in the book. We'll look at everything from its place in the universe right down to its internal structure.
So yeah, we're going way back, billions of years. We'll touch on cosmology, the solar system, how planets form, Earth's really early history, all from those first crucial chapters. Ready to jump in.
Let's do it. Chapter 1 starts with cosmology, the birth of the Earth. And it kicks off by looking at how our view of the universe has changed over time.
Ugh, right. For ages, everyone thought Earth was the center, didn't they? The geocentric view, Ptolemy and all that.
That was the dominant idea for centuries, yeah. Earth smack bang in the middle.
Those complex models with spheres turning around us,
Yeah.
you can see why people thought that way. So what changed? What knocked us off that pedestal?
Well, the Renaissance was a big turning point. You had thinkers like Copernicus, then Galileo, starting to push the heliocentric idea, sun at the center.
Not Earth. That must have been a huge deal back then.
Oh, massive.
Mhm.
It wasn't just a small adjustment. It forced people to completely rethink our place in everything. And Galileo, using the telescope that was key, seeing things like Jupiter's moons, phases of Venus, it provided actual evidence.
Evidence that we weren't the center of it all, just a planet going around a star.
Exactly. And that shift was crucial. It opened the door to understanding the true scale of the cosmos.
And that scale is just mind-blowing, isn't it? Once we started looking outwards properly.
Absolutely staggering. We realized Earth wasn't the whole show. We're in a galaxy, the Milky Way, a giant spiral with, 300 billion stars? Something like that?
300 billion. And it's 100,000 light years across just our galaxy.
That's the one. And our galaxy is just one of,
Yeah.
well, estimates are now trillions of galaxies in the observable universe.
Trillions.
It's almost impossible to picture. And our solar system, even with the sun being like 99.8% of everything,
Yeah.
it's tiny in comparison.
A tiny speck, relatively speaking. You've got the sun, the 8 planets, all their moons, asteroids whizzing about, mainly in the asteroid belt.
And then the Kuiper Belt further out, the Oort cloud way beyond that.
Yeah.
Dwarf planets like Pluto,
Yeah.
comets.
Right. And the planets themselves fall into 2 main groups. You've got the inner rocky ones, the terrestrial planets, Mercury, Venus, Earth, Mars.
Our neighborhood.
Then the outer giants. Jupiter and Saturn are the gas giants, mostly hydrogen and helium. And Uranus and Neptune are the ice giants with more frozen stuff like water, methane, ammonia. And it's not just our system, is it? We keep finding planets around other stars, exoplanets. Thousands of them now.
Thousands confirmed, yeah. Telescopes like Kepler have just revolutionized that field. Estimates suggest there could be billions of Earth-sized planets just in our Milky Way.
Billions. Which really underlines that Earth isn't necessarily unique in being a planet, maybe just unique in its conditions.
Precisely. It makes you wonder what makes a planet habitable. And understanding Earth's own story is key to figuring that out.
Oh, you're talking about these vast distances. Light years. That's the unit we use, right? Because kilometers just don't cut it.
Exactly. A light year is just the distance light zips across in 1 year. It's a way to handle these enormous scales. And it's amazing, even ancient thinkers like Eratosthenes figured out Earth size pretty accurately.
Yeah, using shadows in different cities. Incredible. How did he do that again? Something about the angle of the sun.
He noticed the sun was directly overhead in one city, but cast a shadow in another city further north at the same time. Using the angle of that shadow and the distance between the cities, boom, geometry gave him the circumference. Pretty clever.
Seriously clever. The book has that scale model too, right? Sun as an orange.
Yeah, that really helps visualize it. Sun's an orange, Earth's a tiny sesame seed 15 meters away.
And the nearest star system, Alpha Centauri.
2,000 kilometers away from that orange. It just shows you how much empty space there is out there.
Wow. And it's not just space, it's motion too. We feel like we're sitting still, but we're really hurtling through space.
Oh yeah, definitely not still. Earth's spinning on its axis super fast, over 1,600 kilometers an hour at the equator. That's faster than sound.
Which is why the sun and stars look like they move across the sky. Box 1.2 in the book talks about that apparent movement.
And then we're orbiting the sun at, about 108,000 kilometers per hour? Takes a year to go around.
30 kilometers every second.
But wait, there's more. The whole solar system is cruising around the center of the Milky Way at something like 720,000 kilometers per hour.
It's dizzying. We're moving in so many ways at once, we just don't feel it.
We really don't. It's all relative motion.
Okay, so all this scale, this movement, it led to a huge discovery about the universe itself, didn't it? The expansion.
Right. The Doppler effect is the key here. You know how a siren sounds higher pitched, coming towards you, and lower going away?
Yeah, the sound waves get squished or stretched.
Light does the same thing. Light from something moving away gets stretched to longer, redder wavelengths. That's the redshift. Moving towards us, it's squished, looks blue shift.
And Edwin Hubble, back in the 1920s, he saw redshift everywhere he looked.
Pretty much, yeah. Looking at distant galaxies, he found their light was consistently redshifted.
Meaning they were moving away from us.
Exactly. And even more importantly, he found that the further away a galaxy was, the faster it was moving away.
Which implies everything's expanding. Space itself is stretching.
That was the conclusion. The expanding universe theory. A fundamental shift in cosmology.
And if it's expanding, you trace that back, does that mean it all started from one point?
That's the core idea of the Big Bang Theory. About 13.8 billion years ago, 13.8 giampus, as geologists like to say, everything, all matter, all energy, was packed into this incredibly tiny, dense point. A singularity.
Hard to even imagine.
Then, bang. Not really an explosion in space, but an expansion of space itself. The start of everything, space and time as we know it.
So just pure energy at first.
In the very, very first fraction of a second. Then, as it expanded and cooled incredibly rapidly, fundamental particles form. And within minutes, you get Big Bang nucleosynthesis.
Nucleosynthesis, making nuclei.
Right. Forming the nuclei of the lightest elements.
Yeah.
Mostly hydrogen and helium, with tiny bits of lithium, the universe's first atoms. Box 1.4 in the book goes into this early element formation.
Okay, so we start with hydrogen and helium, lots of it. But how do we get from that to, well, everything else? Stars, planets, us.
Gravity. Over millions of years, gravity started pulling these vast clouds of hydrogen and helium nebulae together.
They collapsed inwards.
Exactly. As they collapsed, they got denser, hotter. Eventually, the core gets so hot and pressurized that nuclear fusion ignites. A star is born. A protostar, initially.
Gee, that's the engine of stars, right? Smashing light atoms together to make heavier ones.
Precisely. Hydrogen fuses into helium, releasing enormous energy. That's stellar nucleosynthesis, making new elements inside stars.
So stars are element factories.
They are. And these first stars, many were probably huge and didn't live very long. When they died, often in massive supernova explosions.
Boom. They scatter all those newly made, heavier elements back out into space.
Exactly. Elements like carbon, oxygen, silicon, all the way up to iron, are forged in stars. And then even heavier elements like gold, uranium. Those are mainly created in the intense conditions of the supernova itself. That's supernova nucleogenesis.
So it's like cosmic recycling. Star guts become the ingredients for the next generation.
It is. Plus, stars constantly shed material through stellar wind during their lives. Our own sun is probably a third, maybe fourth or fifth generation star, formed from material enriched by previous stars. Table 1.1 shows the abundance of elements now, still mostly hydrogen and helium, but with that vital sprinkle of heavier stuff.
Amazing. The iron in our blood, the calcium in our bones. Literally star stuff.
Makes you think, doesn't it?
Yeah.
All those violent events billions of years ago laid the groundwork for Earth.
And our solar system formed from one of these enriched clouds, right? That's the nebular theory.
Correct. Sometimes called the condensation theory, too. You start with this spinning nebula of gas and dust, hydrogen, helium, and those heavier elements.
And gravity pulls it together?
Gravity causes it to contract and flatten into a spinning disk, the protoplanetary disk, with the protosun forming in the hot, dense center. Then, within that disk, tiny particles start sticking together. Dust grains, ice crystals.
Humping up.
Yeah, through collisions, static electricity maybe. Then gravity takes over as they get bigger. They grow into planetesimals, kilometer-sized bodies. The geology at a glance, spread on pages 34-35, gives a great visual of these stages.
So you've got this disk spinning, hot in the middle, colder further out. That must affect what kind of stuff clumps together where. Figure 1.15 shows that temperature difference.
Absolutely crucial. Close to the hot protosun, only materials with high melting points could condense refractory materials. Think metals, rocky silicates.
So the inner planets, Mercury, Venus, Earth, Mars, formed from that rocky metallic stuff.
Exactly. Further out, beyond what we call the frost line, it was cold enough for volatile materials, water ice, methane ice, ammonia ice, to condense as well.
Ah, so the outer planets got started with those icy planetesimals.
Right. They could grow much bigger because there was just more solid material available, rock and ice. And once they got big enough, their gravity was strong enough to pull in huge amounts of the surrounding hydrogen and helium gas.
Which is why Jupiter and Saturn are gas giants, and Uranus and Neptune are ice giants further out. It all depended on temperature and location in that initial disk.
That's the core idea. It explains the basic layout of our solar system really well.
Okay, so a proto-Earth forms in the inner solar system, a ball of rock and metal. But it wasn't layered like it is today, was it? It was just a jumble initially.
Pretty much, yeah. A more or less homogeneous mixture. But then came differentiation. That's a really key process.
Differentiation, meaning it separated out.
Exactly. Early Earth got incredibly hot. Partly from all the impacts, kinetic energy turning into heat, and partly from the decay of radioactive elements trapped inside.
Hot enough to melt.
Hot enough for the iron and nickel to melt. And because metal is much denser than rock, it sank towards the center under gravity.
Forming the core.
Right, a dense metallic core.
Mm.
Meanwhile, the lighter silicate material effectively floated upwards to form the mantle and eventually the crust. Figure 1.16 illustrates this separation beautifully. That's how we got our basic layered structure.
Core, mantle, crust. Okay. And then the moon. Its origin story is pretty dramatic, isn't it? The giant impact hypothesis.
It really is. The leading theory is that quite early on, maybe around 4.5 billion years ago, a protoplanet, roughly the size of Mars, smashed into the still-forming Earth.
A massive collision.
Huge. It would have ejected a colossal amount of vaporized rock and debris, mostly from Earth's mantle, into orbit around Earth.
And that debris eventually clumped together to form the moon.
That's the idea. It accreted over time, pulled together by gravity to form our moon. Probably much closer to Earth initially than it is now.
Wow. What a beginning. Okay, so we have a layered Earth, we have a moon. What about the air and water, the atmosphere and oceans?
Good question. Earth's very first atmosphere was probably just hydrogen and helium captured from the nebula. But being so light, and with early Earth being hot, that atmosphere mostly escaped into space.
Didn't stick around.
Nope. The atmosphere we think of came later, mainly from outgassing, volcanoes erupting, releasing gases trapped inside the Earth.
What kind of gases?
Things like water vapor, lots of it. Carbon dioxide, ammonia, methane, maybe some nitrogen. Comets hitting Earth might have delivered some water and other volatiles too.
So a very different atmosphere from today. No oxygen. Smelly.
Definitely no significant oxygen yet, and probably pretty toxic by our standards. Lots of CO2, water vapor, maybe sulfur gases. As Earth cooled, that water vapor condensed.
It started raining.
Raining and raining and raining for potentially millions of years, filling up the low-lying basins to form the first oceans.
And the oceans then absorbed a lot of the CO2.
Exactly. Carbon dioxide dissolves well in water. A lot of it got locked up in the oceans and eventually precipitated out as carbon and rocks on the seafloor. Nitrogen, being less reactive, gradually became the most abundant gas left.
And oxygen came much, much later.
Much later. Significant oxygen didn't really build up until photosynthesis got going in a big way, maybe only around 600 million years ago. That's a whole other story, covered later in the book, chapter 13, I think. But yeah, the early atmosphere was oxygen poor.
It's amazing how it all fits together. The geology creates the conditions for the oceans and atmosphere. Even the shape of the planet basically round. Why is that?
Gravity again. Once a planetary body gets massive enough and its interior is hot enough to be slightly soft or ductile.
Like taffy?
Kind of, yeah, over long timescales. Gravity pulls everything equally towards the center. And the most efficient shape for that, the lowest energy state, is a sphere, or very nearly a sphere. Figure 1.16 shows this happening alongside differentiation.
Makes sense. Okay, one last thing from chapter 1, meteorite impacts. That early solar system sounds like a dangerous place.
It was a cosmic shooting gallery. Lots of leftover planetesimals and debris flying around, constantly colliding with the young planets. That bombardment tapered off over time, but it definitely happened.
And we still see the scars, right? Craters.
Absolutely. Most small meteors burn up in our atmosphere today, but bigger ones make it through. The book points out meteor crater in Arizona relatively young, easy to see.
I've seen pictures of that one. It's huge.
It is impressive, about 1.1 kilometers across. And then there's a much older, much larger Manicouagan crater in Canada. It's now filled by a lake about 65 kilometers across. Evidence of a really massive impact. long ago.
And the book gives the coordinates for those and the see for yourself bits.
Yep. Latitude 35 degrees, 137.17 N. Longitude 1.120.17 hours for meteor crater. Latitude 51 degrees, 1950.077 N. Longitude 68 degrees, 49.96 hours for Manicouagan. You could literally go look them up on Google Earth.
That's brilliant. Really connects the concepts to real places. And those geology at a glance spreads sound useful too, like the one on forming the solar system.
They really are great visual summaries that pull together a lot of information. Very helpful learning tools.
Okay, so that wraps up the cosmic origins and early Earth from Chapter 1. Huge amount of ground covered. Now Chapter 2, the Earth from surface to center. This zooms in on the planet itself.
Exactly. Chapter 2 gets into the nitty-gritty of Earth's internal structure and composition. We already touched on the main layers formed by differentiation.
The core, mantle, and crust.
Right. The core at the center, super dense, mostly iron and nickel. It's actually got a solid inner core and a liquid outer core.
Liquid metal swirling around down there.
That's the picture, yeah. Then surrounding the core is the mantle. Takes up most of Earth's volume. It's mostly solid rock, but it can flow very slowly over geologic time. And part of the upper mantle, the asthenosphere, is partially molten or weaker.
And the crust is the thin outer skin we live on.
The very thin, rocky layer. And there are two types. The denser oceanic crust under the oceans, and the thicker, less dense continental crust that makes up the land masses.
How do we even know all this? We can't exactly drill down to the core. Seems impossible.
It would be impossible to drill, but we use indirect evidence. The key is seismic waves, the energy waves released by earthquakes.
Ah, right. You mentioned that briefly.
Yeah. As these waves travel through the Earth, they speed up, slow down, bounce off boundaries, or get bent refracted depending on the material they pass through. It's density, whether it's solid or liquid.
So by tracking earthquake waves all over the globe.
Exactly. Scientists can build up a detailed picture of Earth's interior structure. It's like giving the planet a CT scan using earthquakes. Chapter 2 and Interlude D go into how this works.
Clever. So it's not just crust and mantle. The book mentions lithosphere and asthenosphere too. How do they fit in? Are they layers?
They're defined more by physical properties, how rigid or soft the rock is, rather than just composition. The lithosphere is the rigid outer shell. It includes all of the crust, plus the very top rigid part of the mantle.
Okay, so crust plus upper mantle equals lithosphere. Rigid.
Right, and below that is the asthenosphere. That's the part of the upper mantle that's hotter and weaker, more ductile. Flow slowly.
So the rigid lithosphere is kind of floating or sliding on the softer asthenosphere.
That's the crucial concept. The lithosphere is broken into plates, and those plates move around on top of the flowing asthenosphere. This is absolutely fundamental for plate tectonics, which we'll get to.
Got it. Rigidity versus ductility is the key difference there. And what powers all this internal action? The heat?
Internal heat is the engine, yes. Heat left over from Earth's formation, plus ongoing heat from radioactive decay inside the planet. Box 2.3 touches on how this heat moves around. This heat drives convection in the mantle, melts rock, and ultimately powers plate tectonics.
Okay, so Chapter 2 lays out the internal structure. Then Chapter 3 is drifting continents and spreading seas. The title alone tells you things are moving.
It definitely signals a shift towards a more dynamic Earth. This chapter bridges the gap from just understanding the layers to understanding how the surface changes. It touches on the historical idea of continental drift.
Before plate tectonics was fully worked out, people like Wegener noticed continents looked like they fitted together, right?
Exactly. Alfred Wegener championed continental drift in the early 20th century. He pointed to the jigsaw puzzle fit, like South America and Africa.
And similar fossils found on both sides of the Atlantic, and matching rock formations.
All that evidence suggested the continents weren't fixed. They must have moved or drifted over time. But Wegener couldn't really explain how they moved convincingly back then.
That came later. Chapter 3 introduces seafloor spreading, right? That sounds like a mechanism for movement.
It was the missing piece. In the mid-20th century, scientists discovered mid-ocean ridges, underwater mountain ranges, where new ocean floor is being created.
Like volcanic activity on the seabed.
Yeah. Magma rises, cools, forms new oceanic crust, and pushes the older crust away on either side, like twin conveyor belts.
So the seafloor itself is spreading outwards from these ridges.
Exactly. And if the seafloor is spreading, it carries the continents along with it. This provided the mechanism for continental drift.
And there was more evidence, too. Something about magnets, magnetic reversals.
Right. The book mentions marine magnetic anomalies. As that new volcanic rock cools at the ridges, iron minerals inside it align with Earth's magnetic field at the time, like tiny compass needles.
Okay.
But Earth's magnetic field flips periodically. North pole becomes South pole, and vice versa. These reversals are recorded in the rocks on the seafloor as stripes of normal and reversed magnetism, parallel to the mid-ocean ridges.
Like a barcode history of magnetic flips.
Pretty much. And the symmetrical pattern of these magnetic stripes on either side of the ridges was incredibly strong evidence for seafloor spreading. It showed the ocean floor was indeed being created at the ridges and moving away.
So Chapter 3 builds the case. Continents move, and seafloor spreading explains how. That sets the stage perfectly for Chapter 4, the way the Earth works, plate tectonics, the big unifying theory.
This is it. As the preface and prelude emphasize, plate tectonics is the central, unifying concept in modern geology. It explains so much about our planet.
So boil it down for us. What's the absolute core idea?
Okay, basically, Earth's rigid outer layer, the lithosphere,
Crust plus upper mantle.
is broken into numerous pieces or plates.
Mhm.
These plates are constantly moving relative to each other, kind of floating and sliding on the softer asthenosphere underneath. The geology at a glance, Earth system feature, shows this overall picture.
And where these plates meet the boundaries, that's where the action happens.
That's where most of the major geological action is concentrated, yeah. Earthquakes, volcanoes, mountain building, it mostly happens at plate boundaries. The preface and prelude really drive this home.
And there are different types of boundaries depending on how the plates are moving.
Three main types. Divergent boundaries, where plates pull apart.
Like the mid-ocean ridges where seafloor spreading happens, new crust forms.
Exactly. Then convergent boundaries, where plates collide.
What happens there?
Depends. If an ocean plate collides with a continent, the denser ocean plate usually dives underneath that subduction, creates deep ocean trenches and volcanic mountain ranges like the Andes.
Okay. And if two continents collide?
You get massive mountain ranges like the Himalayas, where India is slammed into Asia, no subduction, just crumpling and stacking up.
Wow. And the third type?
Transform boundaries. That's where plates slide horizontally past each other.
Like the San Andreas Fault in California. Lots of earthquakes.
Precisely. Lots of friction. So stress builds up and releases as earthquakes. So divergent, convergent, transform those interactions, explain a huge amount of Earth's surface features and activity. The geology at a glance on plate tectonics, probably pages 110, 111, would visually summarize all this.
It really ties everything together. Mountains, volcanoes, earthquakes. They're not just random events, they're consequences of these moving plates.
That's the power of the theory.
And looking back at these first few chapters, the book keeps hitting on some key themes, doesn't it? Like plate tectonics being the big idea.
Definitely. And the idea of the Earth as a system, how the internal processes, like volcanism driven by internal heat, create the atmosphere and oceans on the surface, it's all interconnected.
Yeah, you can't really understand one part without seeing how it connects to the others. And the time scale, 4.56 billion years. You need that deep time for continents to drift thousands of kilometers.
Absolutely. Geologic change is often slow, but over millions and billions of years, it adds up to dramatic transformations. That theme of change over geologic time is central.
And the interplay between Earth's internal heat driving tectonics and volcanism, and the sun's external energy driving weather and erosion on the surface.
Right, those internal and external engines constantly shaping the planet.
The book also mentions linking geology to natural hazards, earthquakes, volcanoes, which makes total sense now, knowing they happen at plate boundaries, and it even hints at life's role later on with oxygen from photosynthesis.
And the idea of science being based on observation, like Eratosthenes measuring Earth, or geologists mapping magnetic stripes on the seafloor, it's all built on evidence. Even looking ahead, the preface mentions geologic materials as resources, another key theme.
It feels like the book isn't just trying to list facts, but tell a story using these themes. And those learning features, like the See for Yourself, Google Earth links for the craters, that's a great way to make it real.
It really is, encouraging you to actively explore and see the evidence for yourself. The preface makes it clear the goal is engagement, using visuals like the geology at a glance, paintings, and online tools like SmartWork 5 to really help you grasp these big ideas.
Well, this has been fantastic. We've gone from the Big Bang, nebulae, star formation, all the way to differentiating planets, the moon's crazy origin, early oceans and atmosphere, and finally, the bedrock theory of plate tectonics. All from the start of Earth, Portrait of a Planet.
It's an epic journey, isn't it? From cosmic scales down to the layers beneath our feet and the forces that shape our world. Unpacking those first few chapters gives you such a foundational understanding. It really highlights the vastness of time and just how dynamic Earth has always been.
It definitely does. And thinking about that violent early history, the constant change, makes you wonder what kind of future changes could be in store for Earth. Are big shifts still possible?
That's a really important takeaway. Understanding the past, understanding these powerful plate tectonic forces that are still very much active today. It gives us a framework for thinking about future earthquakes, volcanic activity, maybe even longer-term changes in continental configurations. The planet isn't static.
And thinking beyond Earth. Does understanding how our own habitable planet formed, the specific steps involved, help us in the search for life elsewhere? Does it tell us what to look for out there?
I think it absolutely does. Knowing the sequence here, the need for the right ingredients, the formation of liquid water, the development of an atmosphere, the role of internal heat and geological activity like plate tectonics and recycling elements, it helps us refine what conditions might be necessary for life on other worlds. We're not just looking for any planet. We're looking for planets with potentially Earth-like histories and processes.
So this deep dive really has given us that essential framework from the start of the book. Earth's origins, its structure, the dawn of plate tectonics. We've definitely covered the core concepts from those initial chapters of Earth. Portrait of a Planet, Sixth Ed.
Absolutely. We've hit the key points laid out in those foundational chapters. And of course, the book goes on to explore minerals, rocks, the details of plate boundaries, mountains, rivers, climate, so much more. But this gives us the essential context for all of that. We've fully covered the origins and early structure as presented here.